So, we're now in the reactor complex, and for more information on this you can turn to pages 3 and 4 of the handout. So, in each reactor, we're reacting the cyclohexene with the hydrogen peroxide in the presence of a phosphotungstic acid and sulfuric acid catalyst. As has previously been mentioned, there are safety concerns around this reaction route, which have been met by the strict limit of a maximum 30% conversion of hydrogen peroxide at any part. Obviously, this means there's a lot of water present in the feed, as well as the fact that in the reaction 4 times as much water is produced as adipic acid. Therefore, with a CSTR operating at product concentration, there's a lot of water present, meaning that a large reactor volume is required, which had to be minimised. So if you look ahead of you, what you'll see is 5 continuously stirred tank reactors of 32.6 metre cubed volume, each operating at 2 bar gauge and 120 degrees C. They're connected in series with a miniature recycle separation stream between them that removes the excess water. So, from one of the reactors, the product enters a decanter. The purpose of this is to remove the cyclohexene and send it to the next reactor in the series. The aqueous phase leaves the decanter and enters a distillation column, which removes the excess water and returns the hydrogen peroxide concentration to 30%. The bottoms from this are then sent to the next reactor, where the process repeats itself. Leaving the 5th reactor, we've achieved a total conversion of 98.6 of the cyclohexene that enters the reaction complex. You'll notice that each of the reactors have been separated by a minimum distance of 60 meters and a concrete partition wall to contain any explosion in the event that it occurs. There's also a card registry on the building to ensure that only authorized personnel can enter. The product leaves the building to the west, where it enters the separation house, or purification house, which my colleague Guillermo will take you through now.
So, in the product purification complex, the main pieces of equipment that we have are 2 crystallizers and a column, distillation column. So, the product from the reactors goes to the first crystallizer, called the crude crystallizer, which operates at 50 degrees and 1 atmosphere. This separates the bulk amount of crystallizes the bulk amount of the adipic acid to a purity of 99.9. The crystals are sent to the packing area at the end that we'll go to in a minute, and the liquid stream goes to the column 6 in page 5 in your handout. Where the formic acid is recovered, 80% recovery of formic acid to avoid the accumulation in the system. Then the stream without the formic acid goes to the second crystallizer seen at the bottom of the 2-level platform, where again the remaining adipic acid is crystallized to again 99.9% and conveyed through screw conveyors to the packing area that we're going into it now. The crystals are stored in 1 ton, half a ton and quarter ton barrels, and then forklifted to the trucks where they are delivered to the customers. The liquid stream from the crystallizers goes to the waste treatment area. That's going to be explained by my colleague.
So we're about to enter the waste treatment section. More technical information about this section will be found in page 7 to 8 in the handout. It should be noted before starting that the aim of this section is to recover the byproduct which is produced in the reaction, which is the glutaric acid, and also to recover and recycle the catalyst and co-catalyst, which are represented by the phosphotungstate and sulfuric acid. This section comprises an ultrafiltration module and a nanofiltration diafiltration modules integrated in series, and 2 weak base and ion exchanges, which can be found at the end of this section. The 2 ion exchange columns with weak base and ion exchanges function to separate the glutaric acid from the waste treatment, the waste effluent, whereas the membrane sections are responsible for the removal of the catalyst and co-catalyst in the recycling to the reactor. These 2 columns operate in a out-of-phase fashion to allow the continuous throughput of the effluent. And once one of these columns is full with glutaric acid and its capacity is depleted to absorb glutaric acid, a regeneration cycle kicks in, which is responsible for the recovery of glutaric acid from the column, and stores which is then stored inside one of the storage tanks, which are placed in the columns that you will see now. Two tanks with nitrogen have been also placed in the section to allow the pressurization of the columns if in the case of particle buildup in the bed of the ion exchangers.